Hi everyone, welcome back. In this video we will learn about voltaic cells, which are also known as galvanic cells. I wanted to show you a video first. I think this instructor really does a great job giving some nice visuals and understanding what it takes to build a voltaic cell, what's the difference between a voltaic cell and an electrolytic cell. And so once we watch this video, we'll go over some of those principles together, review over them again, and we will work a problem illustrating a voltaic cell based on a redox reaction.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 34, which is on electrochemistry. In electrochemistry, what we're doing is generating current. We're actually generating moving electrons in a reaction, or we're requiring those. And so if you don't understand what a redox reaction is, you may want to look at that video. But a great example of electrochemistry could be a lemon battery. All we're doing is inserting two pieces of metal into the lemon, and we're going to generate voltage. Now, you'd have to hook it up to a pretty sensitive voltmeter to measure that voltage, but if we hook a number of lemon batteries up in series, we could actually light a little LED. And so electrochemistry is really the study of redox reactions, and we're separating the reduction and the oxidation portion in space or time. Now, when you do that properly, you've created something called an electrochemical cell. That cell could either be a galvanic cell. It's sometimes also referred to as a voltaic cell. An example could be a battery, and that's going to generate current. Or we could have an electrolytic cell, and that's going to require current. An example could be a rechargeable battery. And so what we're doing, remember, is separating the reduction and the oxidation. In review, reduction is the gaining of electrons, and oxidation is the losing of those electrons. And what we're doing is tapping the flow of those electrons. Now, the metal is either a cathode or an anode. And a quick way to remember that is that reduction always occurs at the cathode and oxidation at the anode. Or a better way to remember that is that the consonants R and C are going to pair, and the vowels, the O and the A, are going to pair as well. And so what we can do is analyze this cell. We can break it down into its two half reactions. We could figure out the potential of those two half reactions and then simply add them together to figure out the standard potential. So how much energy that cell could produce or require if it's electrolytic. Now this would be at STP, standard temperature and pressure. And so if we have variance from that, then we could use Le Chatelier's principle to qualitatively measure what's going on. We can also measure stoichiometry in a cell. So we could use Faraday's laws to qualitative measure that as well. And so let's start with a simple demonstration. Let's say we take zinc solid and we immerse it in a copper solution. What will happen over time is we're going to get a reaction. And what you're going to find is that zinc is going to start to become an ion dissolved in the solution, and the copper is going to start to form a solid. So you'll actually form this solid copper on the outside. And so that's a redox reaction. It's reduction, it's oxidation. There's electrons flowing there, but we're not tapping any of those electrons. And so this would be that whole redox reaction. Again, we have the zinc, which is losing those electrons, and the copper, which is gaining those electrons. And so if we break it down into its two half reactions, it's going to look like this. Oxidation is where the zinc is losing its electrons, and the copper is gaining those electrons. Those are the two parts. And so in a cell, what we try to do is separate those. But before I actually show you the cell, I want to talk about the reduction potential. In other words, that's the potential energy that can really be released in a reaction like this. And so the zinc being oxidized is like a waterfall. In other words, it has energy up here, and it's releasing that energy. And we could measure it as 0.76 volts. And so you could look up standard reduction potentials, and you'll find a list of these for a number of different reduction and oxidation reactions. Now, the cool thing is if we run it in the other direction, then it would be negative 7.6 volts. In other words, it'd be like trying to move the water up again. It require that energy. So if we look at the reduction part, this copper gaining of electrons, it's going to have a reduction potential, or an E naught, of 0.34 volts. Okay, now let's actually build that cell. Let's separate the reduction and the oxidation portion. And so over here we have the anode. That's going to be where that oxidation takes place, that oxidation of the zinc. And then we have the cathode, and they're each going to be in a different solution. So right here, we've got copper metal in a copper solution. And then over here, we have zinc ions in a zinc, zinc solid in a zinc solution. And if we just let it sit like this, nothing will happen. In other words, it's not going to generate any voltage if we had a little voltmeter here up at the top. And the reason why is that we haven't completed the circuit. And so to do that, we're actually going to have to add a salt bridge. A salt bridge is going to be filled lots of times with a gel. In this case, we've got sodium nitrate. And what it's going to do is it's going to allow the ions to actually flow. So once we've added the salt bridge, this thing's going to turn on. And electrons are going to flow from the anode to the cathode. In other words, the electrons that are being lost in this zinc metal as the zinc becomes a zinc ion are going to travel through the wire to the cathode, where they're going to actually pick up those electrons. And so let's talk about what's going on over here on the anode. This zinc metal, this zinc solid, is actually moving off into an ion in the solution itself. As it does that, it's losing those electrons. And so it's also losing mass. In other words, this anode is going to lose mass over time. If we look over on the other side, the cathode is actually going to gain mass because that copper that's in solution is going to combine with those electrons that are coming over from the anode, and it's going to form a copper metal. And so we could see that the voltage is 1.1 volts. How did I get that 1.1 volts? I simply added up the reduction potential of those two half reactions. Now, how long is this going to occur? It's going to occur until it reaches some kind of an equilibrium, and so it won't last forever. Now, there's a Nernst equation you could use to analyze what happens if it's not really at standard potential, but that's outside the level of AP chemistry. What you should really use is Le Chatelier's principle. So what would happen, for example, if we increase the amount of zinc on this solution? That would slow this reaction. Or if we were to increase the amount of copper, it's going to speed up this reaction. What happens if we increase the temperature? That's going to speed up the chemistry. It's going to speed up this reaction, and it's going to be quicker. In other words, we're going to generate more volts than we would if it was at a cold temperature. And so you should qualitatively kind of understand how a chemical reaction, or things that would affect a chemical reaction, could convert to things that would affect this cell. Now, what's an electrolytic cell? It's really essentially the opposite of that. In this one, what we're going to do is add current. In this case, we're adding a battery on this side, and we're actually going to cause electrons to flow. Great example of this could be electroplating, when we're actually adding one metal to the other side. Another example could be rechargeable batteries. So a rechargeable battery works is you hook it up to electricity, and what it does is it acts as an electrolytic cell. It's going to store energy inside the cell. Now you unplug it from electricity, and now it becomes a galvanic cell. It can actually release energy. And so we can also use Faraday's laws to really study stoichiometry. In other words, what's happening to changes in the mass. And there are two laws. The first one is an equivalence between electricity and the mass. In other words, the more electricity that we apply to a cell, it's directly related to the amount of mass that a cathode or an anode is going to gain or lose. We also have an equivalence in Faraday's second law to the mass loss is going to be equivalent to the equivalent weight of that cathode or anode. What does that mean? Well, if we have something like copper and silver as two of our electrodes, what we would find is that silver, since it has a higher molecular weight, is going to actually lose more mass over time. And so that shouldn't seem surprising if you're looking at it as the losing of atoms from either the anode or the cathode. And so you should have learned the following. Did you learn to analyze data from galvanic or electrolytic cells? In other words, can you identify what is the reduction part and what is the oxidation part? And then finally, could you apply half reactions? Again, we did that with reduction potential or Faraday's law to see what's going on in a cell. Well, if you did, you learned what I hoped you would learn, and I hope that was helpful.
So I just really like the illustrations that he used. And in fact, if you're in my class and in your textbook is the figure for the Voltaic cell with the zinc and the copper that he went over. So we saw in the video that zinc has a tendency to transfer those electrons to copper. So we can see that the oxidation of zinc is occurring at the anode. And those electrons are traveling, once we've complete the circuit with the salt bridge, all the way over to the copper where reduction is taking place. And remember, reduction is a gain of electrons. And the flow of ions within the salt bridge helps to neutralize the charge buildup, because as these electrons are leaving, you can imagine that this is getting a positive charge buildup on the zinc side and a negative charge buildup on the copper side. But that's why you must have that salt bridge to complete the circuit. All right, so therefore, in a voltaic cell, in which direction do electrons flow? Well, they flow from higher potential energy to lower potential energy. And I liked how he used that example of a waterfall. I'll show you also a couple of examples on the next slide. And in addition, it's important to remember that the electrons travel from anode to cathode. And that oxidation occurs at the anode and reduction occurs at the cathode. It's very important that you remember these fundamental principles regarding a voltaic cell, because you will utilize this information and knowledge to calculate electrochemical cell potentials. In a future video, I'll teach you that. So it's important that you can identify oxidation occurs at the anode, reduction occurs at the cathode, electrons travel from anode to cathode. What is the purpose of the salt bridge? The salt bridge completes the circuit. Allowing electrons to flow. Just wanted to give you an analogy of an electrode potential. Just as water flows downhill in response to a difference in gravitational potential energy, electrons flow through a conductor in response to an electrical potential difference, creating that electric current, right? From higher potential energy to lower potential energy. We can imagine if we have water in this beaker apparatus here, that it would flow until it would equalize there. So how do electrolytic cells differ from voltaic cells? So we will discuss that at the end of this video series. We won't study electrolytic cells extensively, but I do want you to know the difference between the two. So we learned that the electrolytic cells are non-spontaneous. And therefore they require an external electric current. And then voltaic cells are spontaneous, so they will just occur spontaneously. So the focus of this chapter in a second semester general and chemistry course will be mainly on voltaic cells. Like, that's what I'm most concerned about in my course. And so yeah, let's go ahead and look at an example. Let's talk about electrochemical cell notation. There's a line notation you can use for these voltaic cells. So we have this redox reaction. If I ask you to do the line notation, then you'll want to write down the half reactions, and so that you can identify what's at the anode and what's at the cathode. And I realize I have the figure below. So, however, I just wanted, before looking at that, so cover this up. Before even looking at that, just dissect the redox reaction as if this were an example word problem on an assessment. And so we know oxidation state of iron is 0, for its neutral element state, and then for this monatomic ion it's +2. And so therefore it's getting more positive, it's losing electrons. So is that oxidation or reduction? Oxidation, remember oil rig. Oxidation is a loss of electrons, reduction is gain. So let's write down that half reaction. The mass is already balanced out for us in this example here, but we need to add electrons to balance out the charge because they had already canceled out when this balanced redox reaction was written in acidic solution. So this has a neutral charge over here, and this has a +10. So how many electrons do I add into which side? Excellent. You want to add 10 electrons. To the product side, which means it's losing 10 electrons, that reemphasizes the fact that we have oxidation taking place. And does oxidation occur at the anode or the cathode? Excellent, at the anode. All right, let's write down the other half reaction. We have the permanganate polyatomic ion here. Now, a question you may have while looking at this is, how did you know this was a half reaction? How did you know that was the other half reaction? So make sure you've watched my video on balancing redox reactions in acidic solution, as well as the other video, which is in basic solution. And what we can see here is that the mass is balanced already. Here, if we just balanced based on the manganese, then we would be missing the oxygens, and so that's why water was added, and then eventually we had to balance out the hydrogens. So that's the reason why these species were included in the half reaction, is to balance out the mass. Now we want to balance out the charge. It looks like we have a +4 on this side. We have 16 minus 2, which is 14. So how many electrons do I need to add into which side? Excellent. You want to add 10 to the reactant side, which means reduction, right? So if the iron's undergoing oxidation, the manganese or the manganate, permanganate is undergoing reduction. And reduction occurs at the cathode. Now, the way we represent this redox equation in the line notation is to first write what is happening at the anode on the left side. I'm just going to go ahead and write this down, and then I'll go over what everything means. All right, so what we have here is on the left side of the double line, we have the anode, whatever is being oxidized. On the right side of the double line, we have what's occurring at the cathode. That double line represents the salt bridge. Anytime you see a single line, basically what you're doing is you're separating substances of different phases, different states of matter. And so we're separating the solid iron from the aqueous iron cation. And then you can see here, if you have multiple species of the same state of matter or phase of matter, then you separate those with commas. So you can see with the permanganate, the hydrogen ion, the manganese cation here too, and they're all aqueous, so they were just included in a row. But then we have water, which is a different state of matter, so that's why there's a bar separating that. And then finally we have the platinum electrode, which is at the very end. Also, when it comes to electrodes, that's what connects the wire together so the electrons can kind of flow through that wire, right? So we always put the electrodes at the very ends of the line notation. And if you have a solid species, like in this case we had iron solid, in the previous example we had zinc solid, we had copper solid. If that's part of your particular redox reaction, then you can use those as your electrodes. But if you don't have something that is solid, so for example, everything was aqueous or liquid here, we had nothing to kind of clamp our wire to, then we had to use a platinum inert electrode. So inert just means unreactive. And so these electrodes are the conductive surface for the electron transfer to take place. So sometimes you'll see graphite used as well. But anyway, so the iron strip is behaving as the anode, and then the platinum on the permanganate side is behaving as the cathode. Okay, so that's really critical to remember, and all comes down to the states of matter. So this is the line notation. So if I were to ever ask you for that on an assessment, this is what I'm looking for to write down. Notice how we don't include the stoichiometric coefficients. We're only writing the species. Definitely write the states of matter. Separate different substances of different phases with single lines. Include the salt bridge between the anode and the cathode. Include the electrodes at the very outside. They should be solid. All right. So let's go ahead and practice. Let's sketch a voltaic cell for the redox reaction below. We'll label the anode and cathode. We'll indicate the half reaction that occurs at each of these electrodes and the species present in each solution. We'll also indicate the electron flow and use line notation to represent the electrochemical cell. All right, so once again, first thing first is kind of identify your oxidation states. So this one is definitely a -1, and then 0 for its neutral, kind of natural form in nature. And so therefore, we are losing electrons for the iodide going to iodine, and so that must be oxidation. So I'm going to write down that half reaction first. And in order to balance out the charge, how many electrons did it lose? It's a -2 over here. It's neutral here. So how many electrons do I need to add? Excellent. So I add 2 electrons to the product side, so that means iodide is losing 2 electrons. This is oxidation, and that occurs at the anode. All right. Now the other half reaction must be the reduction taking place. So let's write down that reaction. And in this case here, we see that it's a -2 charge on this side and neutral over here. So how many electrons do I need to add into which side? Excellent. You need to add 2 electrons to the reactant side. Reactant means that this is gaining electrons and undergoing reduction. Reduction occurs at the cathode. So always use your knowledge of oxidation states to help you identify what's being oxidized, what's being reduced. Separate out the half reactions so you know how many electrons are being transferred from anode to cathode. And then we need to draw it out. So you can draw out your 2 beakers right next to each other, kind of designing our own voltaic cell or galvanic cell together. I like to write the anode on the left side and the cathode on the right. Doesn't really matter, but if we're just making the electrons consistently going from left to right, then you want the anode on the left side. You also want to draw the electrodes, whatever they may be. We just know we need some sort of conductive surface here for the electrons to transfer. So those are my electrodes, and they're always connected by some sort of wire hooked up to a voltmeter. And there we go. We can't forget our salt bridge, and I've seen salt bridges made of all sorts of things. Potassium nitrate's really common, but I've even seen people use bologna, so whatever floats your boat. All right, so potassium nitrate, that's the salt bridge here. We know that the electrons are going from anode to cathode. So we can just kind of point those arrows, they're moving this way. And now we want to identify more specifically what are our electrodes and what's in solution. So we definitely have a solution. So we can imagine that solution, everything's submerged in the solution, the salt bridge and the electrodes, right? And in that solution, we definitely have the aqueous, right? We have the aqueous ions here, and so that's the iodide, and then the ClO2 minus here. Now you'll notice it's really important to kind of be aware of your states of matter, and you're like, all right, well, I have a gas. If that happens, then you will need a tube to go over your electrode to pump the gas in. So let's draw that tube. Kind of over here, it kind of goes, and it's also submerged. And so it covers the electrode and it's submerged, so the gas comes in and gets bubbled into the solution. The gas in this case is the ClO2 gas here. So it goes in here, gets bubbled into the solution to participate in the redox reaction. And then we notice that iodine is a solid electrode here. It turns out that iodine is special, that you need to have an iodine couple with platinum electrode to create this voltaic cell. It's not just iodine alone. And part of that is due to iodine's qualities of just it can sublime at certain temperatures. So maybe the platinum helps to make it a little bit more conductive. And definitely it's a pretty poor conductor of electricity, right? It's a non-metal. And so the platinum helps with that issue as well. Whereas the iron electrodes, zinc and copper, those are metals. They're highly conductive. So we don't need to make it into an alloy with platinum, so you say there. All right, so we have our electrode there and the design of our voltaic cell. So we want to write the line notation to represent the electrochemical cell. So I'm going to start with the anode, the electrode on the outside. So once again, we use the platinum to help make iodine more conductive since it's a nonmetal, even though it's a solid. We know that nonmetals are not good conductors. Separate out the phases. So those were solids. This is aqueous. Represent the salt bridge here. And then we have the gas and the aqueous anion here. And then finally, we definitely needed a platinum electrode on this side as well. And so this shows you an example of investigating a redox reaction and designing a voltaic cell based on your knowledge of identifying what is being oxidized, what's being reduced, and with an understanding that oxidation occurs at the anode, reduction occurs at the cathode. And so make sure you feel comfortable designing a voltaic cell, drawing it out yourself, Don't forget your salt bridge to complete this circuit, as well as showing those electrons going from the anode to cathode. If you have a gaseous species, then you always use like a tube, and it has to cover the electrode and be submerged in the solution so that the transferring electrons takes place. As well as if you have a non-metal solid like iodine, it does need to be coupled with platinum in order to have that conductive surface. All right, thank you all for watching, and I'll see you next time.